Hi everyone, let's solve this question. This was a very good question which was asked in written test of some IIT. Okay, it was asked in written test of some IIT for M.tech admission. So, like in this question, I have written that you need to determine T on such that your transistor are never entering into saturation region. Okay, never entering into saturation region. What do you understand by this line? Your transistor never enter into saturation. That means your transistor have two options. It can go into active, it can go into cutoff as well. Your transistor have two options, active and cutoff. What did they ask? They said that your transistor should never leave the active region. The same question is there, just the language difference is there. In the language they wrote that transistor never leave the active region. What do you understand by this line? Never leaving active region means it should stay in active only. It cannot go into cutoff, it cannot go into saturation. But in this particular problem, the transistor will go into cutoff region. So that was the error. So let's solve the correct question. Let's solve this one. And yeah, before starting the solution, let me clear one thing that I am not offending anyone, neither I am disrespecting anyone here. Okay, I know this question is solved by some other educators as well, and he is like very talented. I highly appreciate him as a teacher. When I was a student as well, I always appreciated him. I always appreciated his teaching. He is very good, and it is really appreciable that he is bringing these kind of questions which no one actually bring. Okay, and yeah, so and that op-amp video I made where I discussed GATE 2024 question. In that as well, I did not mean to offend anyone or disrespect anyone there. Like I have great respect for all the teachers who teaches, right? So yeah, in one of the video, I saw like sir, I thought sir is taking some offense, but I never intended that. I have huge respect for him, and I also like get to learn a lot of new things from him. So yeah, so let's start the solution. And like there are some people who may claim that you are copying the solution of some educators or anything like that. No, I'm not doing it. I have solved the same kind of question in my YouTube channel 1 year back. Okay, you can see it. The same circuit I have solved 1 year back. So hopefully no one will say that I am copying. Okay, yeah. So yeah, with this, let's start the solution and let's see how we will solve these kind of questions and what was different in this question. Okay, so let's start the solution. So transistors are given, input waveform is given, your capacitor is initially charged to 5 volt. And capacitor is initially charged to 5 volt. The input to Q1 transistor is shown. Input to Q1 transistor is shown. You have to determine T on such that your transistor never enter into saturation region even after arbitrarily long time. Okay. So for this is your T equals to 0. This is your T equals to 0. Let's just call this time as T1, this time as T2. So basically T1 is equals to T1 only, right? So capacitor is initially having 5 volt. So you don't need to analyze the previous stage. For T less than 0, you don't need to analyze that. Why you don't need to analyze that? Because they have given your capacitor has initial voltage of 5 volt. No matter what was happening before T less than 0, you don't need to analyze that. They have already given capacitor is having 5 volt. So we will analyze the circuit from T greater than 0 only. Generally, we start analyzing the circuit from T equals to minus infinity. But here they have given the initial condition, that is that your capacitor is having 5 volt. So we will start the circuit from there for T equals to 0 plus. So let's see what is happening at T equals to 0 plus. So this node is VC and this is having 5 volt at T equals to 0 plus. At T equals to 0 plus. What is the input? Input is 3.7 volt at T equals to 0 plus. This input is 3.7 volt. This input is 3.7 volt. What is VB potential? That is 0.7. So what will be this potential? That will be 3 volt. So what will be the current here? 1 milliampere, right? And this is P and P, from P to N. So what this potential will be? This will be 0.7. So what will be the current here? This will be 8 volt. So current here would be 2 by 4. That would be 0.5 milliampere, right? Now this capacitor is charged to 5 volt. Now what is happening from the upward direction? 0.5 milliampere current is coming, and in the downward direction there is 1 milliampere current. Beta is equals to infinity, you can take. So this same current will be flowing here and the same current will be flowing here, and this is your capacitor. This is your capacitor. This I am calling VC. From upward direction 0.5 ampere current is coming, and from downward direction 1 milliampere current is going there. So what do you think, what would be happening? 0.5 milliampere current would be flowing in this direction. Say yes or no. This capacitor would be driving 0.5 milliampere current, right? 0.5 from upward, 1 milliampere is going down. That means 0.5 would be coming from this side. Say yes or no. So what is happening at VC? VC will be charging in this direction from down to up. That means eventually VC potential is going low. Are you getting this point or not? This was 7.3, this was 0.7. So 0.5 milliampere here, 1 milliampere current is here, right? So that means capacitor is driving fixed 0.5 milliampere current. The current is fixed because this node is fixed, this node is also fixed. After t equals to t1, the input will change. The input will change, but we are not seeing that condition. We are only seeing at t equals to 0 plus. So at t equals to 0 plus, 0.5 milliampere, 1 milliampere, capacitor is driving 0.5 milliampere current. So that is a fixed current. So now capacitor voltage will increase, but from the downward direction it will increase. So eventually VC is going down. So what is the equation of VC? VC would be, initially it was having 5 volt. It was having 5 volt in this direction. Initially it was having 5 volt in this direction. So what will be the VCT equation? Initial voltage was 5 volt. Then it was going down by a constant current. If the voltage goes down by the constant current, what is the voltage equation? IT by C. So what is I here? That is 0.5 milli into time t by C. Capacitance voltage is 10 nano. Right. So this is how VCT potential is going down. VCT potential is going down. From 5 to some potential it is going down. We don't know what is that potential, but it will always keep on going down until t equals to t1, which is equals to t1 only. So until t equals to t1, it will go down. From 5 to some particular potential, it will go down, right? This is your VCT. Now let's make the BJTs. So let's do it on the next page. So upper one was your Q2. This was your P, this was your N, this was your P. This node was at how much potential? 8 volt, right? This node was at 8 volt. This node was at 7.3 volt. And this node was at how much potential? P potential. This is the potential equals to VC. This node is at VC only, right? So this is VC. What about this one? This was N, P, N. So P was at 3.7 and this was at 3 volt and this was at VC, right? Now what is happening? VC is going down. VC is going down. VC is going down. If VC goes down, then what is the scene? This is already forward biased because P is at higher potential, N is at lower potential. So your emitter junction is forward biased. Emitter junction is forward biased. You have no issue with that. Here also, this is forward bias. Forward bias. Your emitter junction is forward biased. What about the collector junction? Let's see the collector junction. This is the collector junction here. So for active region, collector junction has to be reverse biased. For active region, collector junction has to be reverse biased. This is the condition, right? We know this condition. For active region, collector junction has to be reverse biased. If VC was 5 volt, initially VC was 5 volt. So P was at 5 volt and N was at 7.3 volt. That means it was at reverse bias only. P was at 5 volt and N was at 7.3. That means N was having more potential. So it was reverse bias. Initially it was reverse bias. So initially it was working in active region. Initially it was working in active region, right? So that we don't need to write. Initially it was reverse bias. What about this one? Initially VC was at 5 volt. VC was at 5 volt. If VC was at 5 volt, that means N was having more potential than P. So this was also reverse bias. So initially this was also in active region. So no doubt about it. Till this point, everything is crystal clear. Now what is happening? This particular VC is going down now. VC is going down. If VC goes down, then what will happen? N potential will go down. From 5 to it will go down to, let's just say, 4. So still it is reverse bias. Let's just say from 5 to it goes down to 3.6. From 5 to it has went down to 3.6. Then what will happen? P will be having more potential, N will be having lesser potential. That means now the collector junction has become forward biased. And this is what you don't want. So if VC is going down, then who is having the problem? Q1 is having the problem. If VC is going down, that means Q1 is moving towards saturation. If VC goes down, then Q1 moves towards saturation because N potential is going down. If N potential is going down, that means forward bias is getting increased. If forward bias is getting increased, that means you are moving towards saturation. So if VC goes down, who has the problem? The problem is with Q1. That means Q1 moves towards saturation. If like here I am writing VC going down. VC going down. So if VC is going down, then Q1 moves towards saturation. What about this one? If VC is going down, that means potential at P is going down. Potential at P is going down. From 5 to it will be 4. So reverse bias is increased, no? N is at 7.3, P is at 4. So reverse bias is increasing only. If P is going down, reverse bias is increasing only. So here reverse bias is increasing. Here reverse bias is increasing. So Q2 has no problem. Q2 has no problem. That means Q2 stays inactive only. Q2 stays inactive. This is the thing for 0 to T1, for 0 to T1. For the time 0 to T1, this is the thing. If VC is going down, Q1 is having the problem. If VC goes down, Q1 is having the problem. If VC goes down, Q2 doesn't have any problem. So this was the analysis for 0 to T1. For 0 to till this time T1, till this time it will keep on going down. After that the input will change. After that input will change. So for 0 to T1, what will be this potential? Can you write down this potential? T1 is equals to T1 only. So VC at T equals to T1. That would be 5 minus, this is 10 to the power minus 8. This will go upward. 5 into 10 to the power 4. 5 into 10 to the power 4 T1. So this potential is 5 minus, this is this potential. That's it. Okay. Now at T equals to T1 plus, what will happen? At T equals to T1 plus. At T equals to T1 plus. What is the input at T equals to T1 plus? Input is 0 volt now. Because this was our input. At T equals to T1 plus, input is 0 volt. Input is 0 volt. And what is your VC? VC here. This VC is somewhat this potential. This is your VC. 5 minus 5 into 10 to the power 4 into T1. This is your VC, that is 5 minus 5 into 10 to the power 4 T1 at T equals to T1 plus, and input is 0. If this is 0, what is the drop here? 0.7 volt. So what this potential will be? Minus 0.7 volt. So what will be the current? Current will be in upward direction. 0 minus 0.7 volt. Current will be in upward direction. Is that possible? No. Q1 will be off. Q1 is off. What did I do? The input is 0 volt. So 0 minus 0.7. So current will be in upward direction. So Q1 will be off. Let's get back to the question. Here what did I write? Never enter into saturation region. So cutoff is acceptable for us. Cutoff is acceptable. That Q1 is never entering into saturation. So cutoff, it is going into cutoff. Then it is acceptable. But if I had written this thing, that transistor never leave the active region, then this condition will not be acceptable, no? So question here becomes irrelevant. Because if input is 0 volt, then certainly it will go into cutoff. But here they are asking that transistor should never leave the active region. It has to leave. There is no other way. It has to leave. Okay, so that was the error in this question, that generally no one noticed this thing, but this should have been noticed, right? So Q1 is off now. If Q1 is off, 7.3 is fixed here, and this potential was 0.7. So this potential would become 8 volt. So this was driving 0.5 milliampere current. In downward direction, what is the current? 0 ampere. Why is it so? Because this was minus 0.7 volt, it would be driving current in the upward direction, which is not possible. So from here 0.5 milliampere current is coming, and this was your capacitor which was having some initial voltage. Now this 0.5 milliampere current is charging this particular capacitor, and this node is VC. So what is happening with VC node now? VC node is going up, because whatever the charge it was having, the more current will increase the voltage, right? The current is flowing in this direction, that will increase the voltage now. This was having this much of charge, it will increase the voltage now. So what will be your VCT? Initial voltage was 5 minus 5 into 10 to the power 4 T on. Now voltage will be increased. The current is 0.5 milliampere divided by IC. IT by C. C is 10 nano. IT by C. And T minus T1 I will write because the circuit is starting from T equals to T1. So what is happening? If I draw the graph, from 5 volt 2 it was going down, then it went down till T equals to T1, then it will go up. How much it will go up, how much it will go down, it depends on the value of T1 and T0, right? How much it goes up, how much it goes down, that we don't know. It depends on the value of T1 and the time period T, because this much time was T1 and this time we are calling T2. This time we are calling T2, and if this much of time I am calling T1 and this much of time I am calling TO. So what will be my T2? T2 will be simply T2 will be simply T1 plus TO. T2 will be T1 plus TO. So what will be your VC? Okay, that doesn't even matter. What will be your VC at this node? That doesn't matter. Okay, even at the potential here, that doesn't matter. Now, what do you understand? From 0 to T1, VC is going down, and from T1 to T2 or T1 to T2, VC is going up. Now, if VC goes up, let's see who has the problem. So let's make the transistors now. Okay, so let's make the Q2 transistor first. This is your Q2 transistor. This node was at 8 volt. Note this is not Q2. And Q2 arrow is here because that is PNP. This was at 7.3 volt and this was at VC. Okay, it was PNP. If VC was going up, if VC goes up, then the positive potential across P is increasing. The positive potential across P is increasing. What does that mean? The forward bias is getting increased. Are you getting this point or not? Let's just say initially P was at 4 volt. So it was at reverse bias only. Now let's just say P becomes 7.4 volt. If P becomes 7.4 volt, then what is happening? If P becomes 7.4 volt, then P is having more potential than N. It would become forward biased. I need it to be reverse biased to make it in active region. But if VC is increasing, then we are moving towards saturation, right? So if VC increases, then Q2 moves towards saturation. I am not making Q1 because Q1 is in cutoff. For this cycle, Q1 is in cutoff. So I am not making Q1 because that will stay in cutoff only. So let's not talk about Q1. So here what is the issue? The issue is Q2 moves towards saturation, right? So what was your complete characteristics? Not the characteristics. What was your VC waveform? The VC waveform was, it started from 5, then it kept going down, then after some particular time it went up. How much it went down, how much it went up, we don't know. This time was T on, then it went up to till this particular time. This window was known as T on, and this window I can call T off. Okay, this time we showed by T1, this time we showed by T2. So eventually T1 is equals to T is equals to T1 plus TO. In this cycle, if VC was going down, who had the problem? Q1. Q1 moves to saturation. And if VC is going up, who has the problem? Q2 moves to saturation, right? Let's just say in this one, capacitor is discharging. Here the capacitor is discharging. And here the capacitor is charging. So let's take the first condition. What is that particular condition? That condition is, let's just say if your discharging is more than charging, discharging is more than charging. If your discharging is more, then what will happen? Your discharging is more. This is your VCT. In every cycle, it discharges more but charges less. This is what I am saying. In every cycle, it discharges more but charges less. Then discharges more and charges less. So after every cycle, what is happening? VC is eventually going down. VC is eventually going down. Here, VC is eventually going down. And if VC eventually goes down, that means Q1 will go into saturation. Are you getting this point or not? I have assumed that if my discharging was more than charging, so it was losing more but gaining lesser. So eventually VC is going down. Slowly after cycle by cycle, VC is going down. Because in the question it is written that we have to analyze for arbitrarily long time. For infinite cycle we have to analyze, not for only one cycle. For infinite cycle, that Q1 and Q2 should never go into saturation. Both of the transistors should never go into saturation. So it is going down, gain lesser, goes more down, gain lesser, goes more down, gain lesser. So eventually VC is going down. So here what did you understand? That Q1 goes into saturation, not moves towards saturation. Q1 goes into saturation. So this is not the desirable condition. Let's take the second one, that if charging is more, then what will happen? If charging is more than discharging, charging is more, then Q2 will move towards saturation, right? Q2 will go into saturation. Because if charging is more, then how will your waveform go? This discharges less, but charges more. Discharges less, but charges more. Discharges less, but charges more. So VC is going up. In this way, your VC is going up. And if VC goes up, that means Q2 goes into saturation. Let's take the final condition. If charging and discharging are equal, if your charging and discharging is equal, is equals to discharging. If charging and discharging equal, then what will happen? This is your VCT versus time t. It discharges, let's just say it discharges by 2 volt. It started from 5, it discharges by 2 volt, that means it has reached to 3 volt. Now it charges by the same amount. It gains 2 volt again, so it will again go to 5 volt. Then again it discharges by the same amount, again it goes to 5 volt. From 5 to again 3, from 3 to again 5. So after every cycle, what is happening? After every cycle, what happens is that this particular potential will remain same, and this also will remain same, right? Whatever that he has lost, whatever the capacitor has lost, it is gaining the same potential. Are you getting this point? Whatever the capacitor has lost, it will gain the same potential, right? Then what does that mean? If it is losing same and gaining same, that means VC after every cycle, VC will remain at that potential only. VC is neither going up, neither going down. So this is the desirable condition. Here Q1 and Q2 both remains in linear. Both doesn't go into saturation. I should write both doesn't go into saturation, because both are not remaining in linear. not linear, I should say active. So both are not remaining in active. One of them is going into cutoff because here it is going into cutoff. So that was the error in this particular question as well. The transistor never leave the active region. No. Transistor should never enter into saturation. Okay. So here I should write both never enters into saturation. So what was the speed of charging for this capacitor? Speed of charging. It was charging with 0.5 milliampere current. It was charging with 0.5 milliampere current in t of time, in this time. In t of time, it was charging with 0.5 milliampere current. So what was the charge it was gaining? 0.5 milli into t of divided by C. And how it was discharging? It was discharging with 0.5 milliampere current as well. It was discharging with 0.5 milliampere current in the time window of t on. So 0.5 into t on by C. 0.5 milli into t on divided by C. So from here, what did you get to know? Your t on is equals to t off. So if t on is equals to t off, then complete t was given. T was given as 1 micro. So what would be your t on? T on would be 1 by 2 microsecond. So this would be the answer of this particular question. Okay. Now we will do one interesting thing, that is very interesting thing. Now what I want to do is that I don't want to change the theory of this question. I want to keep the theory of the question as it is. The transistor never leave the active region. So what changes I should do? What changes I should do in the circuit? In the circuit, what changes I should do? I don't want to change the theory. So what changes I should do in the circuit? Instead of this ground, I should apply some potential Vx, and that potential should be, when it is T on, this potential, let's just say this Vx is minus 1.4 volt. This Vx is minus 1.4 volt. Better I should make it with red pen. So I am making one Vx potential as well. What is this Vx potential? For time window T on, it is minus 1.4. And for time window T off, it is 0. Are you getting this point? For this window of T on, it is minus 1.4 volt. For time T off, it is 0 volt. Then minus 1.4, 0. So what will happen in this one? What will happen? When Vin is equals to 3.7 volt, when Vin is equals to 3.7 volt, at that time what will happen? The capacitor will discharge with 0.5 milliampere current, right? 0.5 milliampere current. And when Vin is equals to 0 volt, when this potential is 0 volt, so what will happen at that time? If this potential is at 0 volt, wait a second. Okay, sorry. This waveform I made it wrong. Sorry. Initially it should be 0, then it should be minus 1.4. 0 and minus 1.4. 0 and minus 1.4. So 0, this is 0 and then minus 1.4. 0 and minus 1.4. Initially it should be 0 volt, and after that it should be minus 1.4 volt. This is your T on, this is your T off. For 0 to T on, it should be 0 volt. 0 to T on, this Vx potential I am talking about. So if it is 0 volt, then 3.7 minus 0.7, that means here it will be 3 volt. It will drive 1 ampere current, and capacitor will discharge with 0.5 milliampere current only, right? And when Vin is equals to 0 volt, when Vin is 0 volt, at that time what will happen? At that time, when Vin is equals to 0 volt, this time window will be 1.4 volt. Okay. This window is T off. This window is T on actually. After T on, when Vin is equals to 0 volt, at that time, this input would become minus 1.4 volt. So here you are having minus 0.7 potential, and here you are having minus 1.4 volt. So this current would be 0.7 by 3 milliampere, right? So what would be happening in the capacitor? From upward direction, 1 milliampere current, not 1 milliampere. Yeah, from upward direction, 0.5 milliampere current is coming. And in the downward direction, you are having 0.7 by 3 milliampere current. So rest of the current would be going in the capacitor. Rest of the current would be going in the capacitor in this direction. Right? In the capacitor, the current would be going in this direction. That current would have been 0.5 minus 0.7 by 3 milliampere. So the capacitor would have been getting charged with this current and getting discharged with 0.5 milliampere. So for never leaving the active region, here it is not going into cutoff. It is in active region only. Here it is not going into cutoff. So for never leaving the active region, the speed of charging and discharging should be same. So 0.5 milliampere. This was happening for t on time. This circuit was there for t on time, right? For t on time. 0.5 milliampere into t on by C. That would be equals to 0.5 minus 0.7 by 3. So it would be in 0.8 by 3. 0.8 milliampere by 3 into T off by C. Right. So from here, what do you get? 1.5 by 0.8 into T on is equals to T off. And the total time window is 1 micro. So what you will get? T on plus 15 by 8 into T on is equals to 1 micro. So answer would have been T on would have been 8 by 23 micro. What is the answer of 8 by 23? By 23, that is 0.35, approximately 0.35, not 0.35, you can write 0.347. So t should be 0.347 microsecond. So this would become a more interesting problem if they had framed it correctly, but there was one error. That was a common error, that they should have changed the language. If they don't want to change the language, then they can change the circuit. In the circuit, they have to make the change that instead of that ground, they have to give a square wave input from 0 to minus 1.4. When t on time, it should be 0. At that time, transistor will be turning on, and for t off time, it should be at minus 1.4 volts, so that the current flows there. If the current is flowing, then the transistor is in active region only, and we have to maintain that particular region. For that, what we are going to do? For that, we have to check that the speed of charging and discharging should be similar. This was the speed of discharging, and that was the speed of charging. Okay, discharging and charging speed is equal. So from there, we get to know that T on timing. So this question would have become more interesting, right? And this was the given question. For the given question, answer would have been this one only. So in the examination, if this particular circuitry is given and the same kind of circuitry is coming, and they have written transistor never leave the active region. If it comes in gate, it will be MTA. But if it is coming in some written test of IITs, then you should be thinking never leave the active region. That means even if it is going in cutoff, it's fine. Even if it is going in cutoff, it's fine. You shouldn't go into saturation region. Okay, well and good, understood everything. So I hope you liked the lecture. Okay, then let's meet you in the next lecture. Thank you.